Welcome to the 15th lecture from chapter number 7. We are studying VLSI design and we are studying transient analysis of CMOS logic gates. In our last lecture, we studied transient analysis of CMOS NAND and CMOS NOR. We also learned how to draw CMOS schematic of a given Boolean expression in one of our previous lectures. In this lecture, we are going to perform transient analysis of a CMOS of a CMOS based circuit. This one, it's a complex Boolean expression. It's neither NAND nor not, nothing. It's a bit difficult expression compared to a 2-input NAND we studied last time, or a 2-input NOR or not. Right. So, what is the CMOS schematic for this given Boolean expression? In our earlier lectures, we learned how to apply De Morgan's law to draw the PMOS array, and then to invert the expression to draw NMOS array for any given Boolean expression in order to implement the schematic of the given Boolean expression. Right. We studied that the first expression is the first step is we apply De Morgan's law. Given this expression, we apply De Morgan's law, and we apply De Morgan's law repeatedly unless the inversion is distributed on each and every variable. Like we have this expression, we apply De Morgan's law. The first step, this distribution, this bar or this inversion is distributed like it is on X, and on this OR expression is OR operation between y and z, and then we apply De Morgan's law once again over this, and now this inversion is distributed on y and z, and the operation is replaced with its dual. This OR operation is now AND. Right, and now we ignore these inversions and implement using PMOS, and this is what we have done. We have y and z ANDed. This means they will be in series. We studied that the AND operation results in series connected transistors, and OR operation results in parallel connected transistors. We studied last time. Right. So this is the equivalent PMOS array, and we also studied that to implement NMOS array, we have to just invert the original expression. This is x dot y or z. This one. So and now if we implement it using NMOS. So y and z, they are in parallel. Y and z. Because there is OR operation in between, so they are in parallel, and this whole is in series with X, ANDed with X. This means in series with X, like this, and we can connect it to the output. Right. This is the full schematic of this Boolean expression, and you can verify its truth table at home. You should get your desired output. You will be able to fulfill or verify the truth table for this Boolean expression. Right. So what is, in order to perform the transient analysis for this circuit, we need to see what is the C out. You know, the C out for any gate is, we studied earlier that C out is the internal FET capacitance plus the load capacitance. The load capacitance is the capacitance of the load this gate is driving at its output. It may be another gate. And the other capacitance is CFET. It is formed by this PMOS because it's connected at the output of this, the drain capacitance of this PMOS transistor, the drain capacitance of this PMOS transistor, CP, and the drain capacitance of this NMOS transistor. So we have now 3 capacitors connected to the output. Therefore, CFET can be written as CP plus another CP plus Cn, that's all, and this Cl. So this hole is CFET for this gate. So C out is 2CP plus Cn plus Cl. The total output capacitance, for this gate. Right. The next is we need to find the rise time delay and the fall time delays. The rise time delay Tr, we know it's generally written as 2.2 R. This is capital P, C out. This capital P is the equivalent resistance of the PMOS array. The full PMOS array containing more than one PMOS transistors. For example, this one containing 3 PMOS transistors. So what we want to do is to find this TR, the rise time delay. TR is written as 2.2 RP C out, and TR worst can be the time when we have this TR at its max value. RP would be max when we have these two transistors on, Y and Z on, because in that case we'll have 2 RP in the path. So 2 RP is of course larger than RP. So it will be offering a resistance RP when X is 1, but when X is 0, when this transistor is on. But when these two transistors are on and this transistor is off, the overall resistance offered by the PMOS array would be 2 times the individual resistance. RP for this, RP for this. If this is off and these two transistors are on, this array would be offering the max resistance, because this is RP plus RP is 2 RP, and the best delay, or the least value of delay, best means the least value of delay, would be offered when we have all these transistors on. These two transistors, 2 RP, this transistor is also on, and it is in the parallel, and it is in parallel with these two transistors. This means that would be 2 RP in parallel with RP, and we know the two parallel transistors, the two parallel resistances, their equivalent is the smaller than the smallest one, the smaller one, RP. So the equivalent would be even smaller than RP, even smaller than RP. So this equivalent is lesser than RP, because when we have two resistors connected in parallel, the result is the smaller than the smaller resistance, and there would be an average rise time delay, and this delay is offered by this PMOS array when we have this, only this RP, only this transistor on, offering RP, and these two transistors are off. So that would not be RP C out, just 1 RP. That would be the average value of the delay, or this value would be in between this worst delay and the best delay. Right, and let's look at the fall time delay for this schematic or for this implementation. The fall time delay, we know that the general expression is TF is 2.2 Rn C out, and we know what is C out. We have just completed C out. Rn is the equivalent resistance offered by the NMOS array. It's not the resistance offered by PMOS, it's the resistance offered by NMOS, the whole NMOS array containing more than one transistors. In this case, there are 3 MNs, 3 NMOS transistors, right? Maybe this has resistance Rn, Rn, and resistance Rn. So, what can be the worst time fall time delay? Worst case fall time delay. TF worst. Let's see what this delay is. Right. The worst case delay is when we have the max path resistance, and that is when we have this on and this on and this is off. Or it can be vice versa. Even this can be off, this can be on. The equivalent resistance of the path would be 2Rn in both cases. So that would be 2.2 times 2Rn C out, the worst case delay. The best case delay would be when we have all these transistors on. When we have all these transistors on, this and this, that would be these 2 transistors, Rn by 2 plus Rn. Rn plus, because why it is Rn by 2? Because we have 2 NMOS transistors connected in parallel having resistance Rn and Rn, and Rn in parallel with Rn is Rn by 2. TF best is this, and what is the average TF? The average, there is no average TF. Either we get the output, we get a 0 at the output through this path or this path, or when they all are on. So there is no average. The average is the same as best. There is no average case. There was an average case in case of rise time delay, but in case of fall time delay, we don't have the third option. Here we have 3 options. In case of PMOS array, we have 3 options, but here we have only 2 options. Right, that's all for this lecture, and the next lecture we will continue studying transient analysis of complex CMOS. Thank you.